Hello, everyone, and thank you for joining us for week 7 of the RISE Institute and Rugby Research Injury Prevention Group 2026 Analytics Series. Now, our first intern to present will be Elan, and she will be presenting on Logistic Regression Overview. Elan, may you please share your screen?
Hi, my name is Alon Cooper. I am a senior kinesiology major at Hampton University, and I'll be presenting on logistic regression. What is logistic regression? It is a formula that predicts the probability of an event that will happen. It's usually calculated through a machine application like Excel or any other Google online calculator that will draw a best fit line between your data points. It analyzes the relationship between the independent variable and the dependent variable. Logistic regression only works for binomial events, meaning that the outcome must be 0 or 1, true or false, yes or no, or any other thing that only has one of two options. Logistic regression is used to measure how relevant the independent variable is for predicting the dependent variable, meaning that if your independent variable is something like smoking, your dependent variable can be lung cancer, and it's going to measure what's the probability in between smoking and getting lung cancer. Each coefficient, which we'll see in the equation that I'll show you in just a moment, can be translated into an odds ratio, which explains how the independent variable affects the outcome or the dependent variable. Logistic regression allows for multiple independent variables, which means that smoking and age might have cause lung cancer. Logistic regression is also very easy to interpret and analyze. Logistic regression, when you're trying to calculate it, you'll clean up your data and into categories like age, smoking habits, injury, things like that. And your dependent variable will be either 0 or 1. Then you'll put that into a calculator and it'll find the log odds of the event, which are all of these coefficients right here, these regression of coefficients. We can determine if the logistic regression performs well by using ROC curves, which another intern will go into a bit later. We can watch this video from 3-Minute Data Science that shows how the graph works and how you can influence the line and the predictability.
Logistic regression is a statistical technique that models the probability of events given one or more independent variables. You'll start with input data that is of any numeric type, but the output variable will be binary. It'll be 0 or 1, indicating a false or a true value, respectively. You then fit this S-shaped curve called the logistic function to this data. It can then be used to make predictions of probability whether or not an event will happen, such as, given so many hours of rain, what is the probability of a flood? Notice how that these points can project themselves onto the logistic function, and we can use maximum likelihood estimation to fit the curve, which we'll talk about shortly. Notice that there are these middle points where there is a mix of true and false cases. If these points follow a transitional trend of increasingly showing an event more likely to happen or not happen, you will see that that S-shaped curve will climb or decrease respectively. We can then leverage it to predict probability between 0 and 1. Let's take a case where we expect 6.2 inches of rain, and this is going to result in a 0.75 or 75% probability of a flood. If we define a threshold, say 0.5, and anything greater than 0.5 will be true, anything less than 0.5 will be false, we will then predict there will be a flood. We can move this threshold based on our needs. For example, if we set it to 0.8, this would actually categorize as false and there won't be a flood. We can also reduce it to say 0.2 and set a much lower barrier to classifying a flood. This is the function that produces that S-shaped curve.
Okay, so as you can see, the graph will always look like this. It'll be 1 on top and 0 as the baseline. And 1 will be if the event does occur, 0 is if the event doesn't, and the probability is in between. Oh. Okay. Logistic regression limitations are that the data points must be independent from each other. And it also requires little to none multicollinearity among the independent variables. That means that the independent variables can't influence each other, meaning that age and smoking can't both cause lung cancer, or like they can't influence each other, if that makes sense. The dependent variable must be nominally scaled, meaning that it can't be ranked or ordered. It has to be something that's labeled. Some real world applications are a lot. You can use logistic regression in a lot of different ways, but some of the ways are you can predict whether emails are spam or important. It'll filter out through your subject line, and that's how it determines that. It can predict different diseases. It can predict medical treatment success. It can predict fraud. And most important to us, it can predict return to play outcomes. So as you can see down here, we have our independent variables like age, gender, and smoking. And then you will get your probability that you will get a disease from doing these things. I think that the most beneficial application for our use will be using our data to predict injuries that might happen later in the day compared to early in the day, or injuries if they have past injuries beforehand. Here are all my references, and thank you so much for listening today.
Thank you for that presentation, Alon. Are there any questions, or does Dr. Lopez, do you want to add anything?
Just really briefly, more importantly, the data has to be super clean. One of the biggest limitations with logistic regression analysis is not only developing your model, but making sure that the data, because it's so sensitive to outliers. Okay, so we'll continue. Thank you. Very good there.
Now, our second intern is Natalia, and she will be presenting on linear regression overview. Natalia, could you please introduce yourself and share your screen?
Thank you so much, Kevin. My name is Natalia. I'm a rising senior at Villanova University, and today I'll be presenting on linear regression. I think my screen should be good. Linear regression, it will be an overview. Well, what is linear regression? Linear regression is a statistical method used to examine the relationship between variables. It helps us understand whether one or more independent variables can explain an outcome, which is a dependent variable. The model fits the best fit line through the data, showing the overall trend. This allows researchers to make predictions and estimate how much a change in one variable affects another. This makes linear regression a valuable tool for identifying relationships and guiding data-driven decisions. Key components of linear regression. So the equation you see is the linear regression equation, and I will break it down on what each variable means. So y is the dependent variable or the outcome that we're trying to predict. X is the independent variable, also known as the predictor. This is a factor that we use to explain or predict the outcome. B1, or slope, tells us how much the outcome changes when the predictor increases by 1 unit. A positive slope means the outcome increases, while a negative slope means the outcome decreases. B0 is the intercept of y. So at this point, y is equal to 0, and x is equal, at this point, B0, the y is equal to 0, which is when it interacts with the x-axis. And lastly, the error term. This is a difference between the actual value and the value predicted by the model. It represents the variation that the regression equation cannot explain. Together, these components make up the relationship and tell us the relationship between the variables. Then you have simple versus multiple linear regressions. In the top picture, you can see a simple linear regression, which only uses one x value to estimate one outcome. In the bottom picture, you see a multiple linear regression, which uses 2 or more predictors to estimate an outcome. They all estimate the same y variable, but you can use it to show different x values. For interpreting linear regression, here are 3 different ways that it would happen. The first one is a positive linear relationship. In this case, as x increases, y tends to increase as well. Next, you have a negative linear relationship. So as x increases, the y trend decreases. And lastly, you have a little to no change. In this case, there is no relationship between the variables, and you would not be able to use linear regression in this case. So this is an example done by Kim and his colleagues in 2021. And in this case, researchers used multiple linear regressions to predict health-related physical fitness. To make these predictions, they use factors such as age, sex, height, weight, and other factors like body mass index to make their predictions. This graph specifically looks at hand grip strength. The x-axis shows how each participant measured their action between the measured and predicted values. The correlation coefficient R equals 0.841 indicates a strong association, and the p-value is less than 0.01, which means the relationship is statistically significant. When to use linear regression. Linear regression can be used in many different aspects. In general, it can help identify trends, predict future outcomes, and estimate how much one variable affects another. In sports medicine, it can be used to predict injury risks, track improvements with physical therapy or rehab, and evaluate how different factors like training load, sleep, and nutrition impact athletic performance. This also allows researchers, regardless of their field, to make evidence-based decisions. When using a linear regression tool, you have to be able to make these assumptions for the linear regression model to be valid. First is normality, which means that the model's prediction should be close to the actual values. If there are many outliers, then you would not be able to use the linear regression model. Next is the equality of variance. The model should be equally concentrated across the graph. You shouldn't have outliers only on one section versus the other. It should be equally spread out. Linearity. The data has to follow a straight line pattern or at least trend in that direction. As I showed in one of my previous slides, it cannot be scattered all around the graph. And lastly, collinearity. Each predictor has to provide different information. If two predictors are too similar, they don't add much value and can impact the results. If these assumptions are not met, the linear regression model may not be reliable. The graph or regression line may not accurately represent what the relationship between the two variables actually is. For the strengths of linear regression, it is very easy to understand and explain, and it can be used to predict future outcomes. It shows the relationship between two variables and helps identify factors that have the greatest influence. Multiple linear regressions can examine several predictors at the same time, which is always very helpful for researchers. For some weaknesses of linear regression, like anything, it does have some limitations. With the assumptions that I discussed earlier, if those are not met, then the results may not be accurate. It works best when the relationship is between variables in a straight line. So going back to if the points are scattered, linear regression would not be the right tool for this. Outliers can really skew the data and affect if it's valid. And predictor variables shouldn't be too similar because they reduce the model's accuracy. Lastly, it shows the relationship, not causation, so one variable does not cause another. To conclude, just some key takeaways of linear regression. It helps us understand the relationship between variables and predict different outcomes. The slope tells us how much an outcome changes as the predictors change. The results are only reliable when assumptions are met, and all the assumptions have to be met in order for it to be reliable, not just some of them. And lastly, it doesn't tell us a cause and effect relationship. It can help us just associate variables together. Here are my references, and if there's any questions. Thank you.
Thank you, Natalia, for that presentation. I want to open the floor to questions, or Dr. Lopez, do you have anything to add on?
No, good. I think you did a great job, and not only that, you covered the weaknesses or the limitations. Obviously, particularly, it's a linear relationship, so you can't. It doesn't do well with curves. So you're kind of limited in that, even though there's a joke there that it's a linear model, right? So the whole idea is that the variables have to be very close in what they're comparing. Okay? Sorry.
Yes.
Go ahead. Thank you.
Thank you for your comment, Dr. Lopez. The next presenter will be me. My name is Kevin Serrano, and today I will be talking about receiver operating characteristic curves, or more commonly known as ROC curves. Okay. Like I said before, my name is Kevin Serrano. I'm a rising sophomore from Brandeis University, and today I will be presenting on receiver operating characteristic ROC curves. So let's get an intro to diagnostic accuracy. We normally conduct clinical or sports science research. We frequently find statistically significant differences between groups. For instance, noting that concussed athletes perform worse on a cognitive battery than healthy controls. However, if we look at the value for a p-value, a low p-value does not automatically mean that a clinical test is ready for the field. We need to keep in mind that there is the group versus the individual. The t-test and p-values look at significance in a population as a whole, while ROC curves are actually the golden standard in order to determine individual patient classifications. ROC curves allow for the ability to have individual level diagnostic analysis and are used for diagnostic and prognostic tests in order to be able to look at every single possible decision threshold. Looking at the ROC curve and the mathematical foundation it has, we're looking at two specific topics, sensitivity and specificity. Sensitivity is looking at the true positive rate, which is calculated by having the true positive values over the true positives plus the false negatives. This is normally plotted on the vertical axis, and this determines the probability that the test is positive given that the disease and injury is present. Next, we look at specificity. This is the value of true negative rate, also known as TNR, which is equal to 1 minus the FPR, or the false positive rate. The specificity is the probability that the test is negative, given that the disease and injury is present. Lastly, we also have to calculate the false positive rate in order to get the specificity. The false positive rate is the false positives over the false positives plus the true negatives. This false FPR rate gives us the probability of a false alarm whenever we are looking at data. Now looking specifically at the table analysis, we can have a confusion matrix. This is where we really look at the predicted values and we are able to find the true positives and the false positive, which is the top two, and we have the false negatives and the true negatives, which are the bottom two. This will allow us to be able to find the data and the values that are associated with our ROC curve. Next, let's look into data to decision. When interpreting the ROC space, remember that the diagonal dashed line, utilizing previously calculated data, construct two overlapping bell curves. As you can see in the middle, we can make these bell curves overlap, and it allows us to have different sections between true negative, true positive, a false negative, and a false positive. Once we have the outline for the physical and conditional metrics on each side, we can see that we can make those distinctions between every single section. Then, using that line in the middle, we can call the decision threshold. We can determine the amount of true negatives, false positives, and true positives within that area. This will allow us to determine whether or not there are different values and will allow us to insert different criteria that may be valid. Now looking more specifically at constructing the ROC curve. When you're interpreting the ROC space, remember that the diagonal dashed line represents random guessing. Any clinical test must perform significantly better than that baseline in order to be viable. As you can see through the red line, anything above that red line, closer to the 1 on the y-axis, is able to be called viable. However, if you're underneath that classifier, most of the time those tests or those examples are actually not viable for the exam. Area under the curve, the AUC. Now, looking at the AUC, or also known as the C index, we can see that it ranges between 0.5 to 1. The area under the curve really helps determine the accuracy of a randomly selected case and if the models can correctly predict injuries and diseases. When looking at the higher AUC, we have a higher classification percentage, basically meaning, looking at the graph, we can see that an AUC at 0.623 is equal to 62.3% classification percentage. Now choosing the optimal threshold. We have two different indexes and equations that will help us determine whether or not the the test that we choose is correct. First, once you've built your ROC curve, you must recommend a specific diagnostic cutoff for clinicians to use. The most common objective is approach is the Unit index, which mathematically identifies the point on a curve furthest from the random guessing line. However, as researchers, we also must consider clinical utility. If a false negative is far more dangerous than a false positive, we should manually shift our cutoff along the curve to favor sensitivity, even if it deviates from the mathematical minimum of the Unit index. Now, looking at some of the common mistakes that people have during ROC curves, we can see that misinterpretation is a very important factor that might lead to mistakes. When you assume that the AUC values are identical, you cannot assume that they're actually relaying the same information. Context is very important when determining the AUC values, when determining whether or not the AUC values are important. Next, you also have to fully plot every single point on both the ROC curves, the AUC, and the bell curves. This will allow for the most accurate representation of the data and really understanding whether or not your individuals are either going to have false positives or any other mentioned previously. Then we also have to utilize the scores for the ROC curve and predictive models. We cannot use the same scores for both of them, or else they will give us overly optimistic curves, meaning that we assume that all of them are going to be true positives instead of really determining whether or not there's variability between the group. These are my references. And thank you. Open for any questions, or Dr. Lopez, do you have anything to add?
So everyone understand, when you look at the curve, you're almost looking at sensitivity and specificity, right? How sensitive it is and how specific it is. Underneath and then sensitivity above. I think those two factors are probably the most important thing you should take from the ROC curve. And if you understand those particular calculations on the curve, I think you should be okay, particularly for any USMLE questions. But we'll talk about that a little bit later. Thank you. Good job there.
Thank you. And with that, we will conclude week 7 of our analytics series. Thank you everyone for joining us.